Okay. It's time to start. So, any question from anything? Otherwise, we'll go through our midterm review. And yeah, so using a detailed midterms, it will be split into, I don't know, 4 or 3. But we'll split into multiple classrooms because there will be too many people. And yeah, some of them will share with the discrete math class. So we'll try to like having you alternating in rows, so so you will have like less problem cheating. Okay. Anyway, if there is no question about material, then let's go through the review. So the review is kind of go through everything. Oh, wait, why is this? Why is it annoying? Wait a second. Let me turn off all this. Procedure now apply to all. And okay, okay, and yeah. So let's go through one by one. So let's start with 1.1, where we talk about solving linear systems. And the first thing we say is the number of solutions of linear systems, it has only 3 possibilities. It's either infinite, 1, or 0. So infinite is consistent and has infinite solution. And it can be considered as a unique solution, that's one solution, or inconsistent, that means there are little solution. And like we talk about equivalent systems who have the same set of solution, and there are systems that can be related by those elementary row operations. So remember, there are 3 elementary row operations. First is exchanging 2 rows. Second is multiplying a row by a non-zero real number. And the third one is replace a row by the sum with, so you add or subtract a row to another row. Yeah. So there are 3 row operations you do, and you can get equivalent system. Then there are coefficient matrix and augmented matrix basically make your, okay, so now this thing to write. So you have your, anyway. Yeah, so you have a linear system like x1 plus a1x1, a11x1. So I just write a something x1, a something x2, equal to b1, and a something x2 plus a. So linear system like this. So a whole bunch of a and a whole bunch of x, and equal to a whole bunch of b. And you can turn those a, so you can turn this equal to ax equal to b. Okay. And this a is the matrix formed by all those small a, and b is a vector formed by those b. Okay. So hopefully we should be all very familiar with this. Okay. And that's 1.1, and 1.2 we give the very important. Turn off this. Okay. Wait, let me edit really quickly. Turn off the animation. Slideshow. Let's see. Show without animation. And select this once again. Okay, should be fine now. Yeah, and then 1.2 we give the most important reason of the course, that's the Gaussian elimination. Okay, so Gaussian elimination is where you do use the elementary row operation. So the 3 things we have here, and we get the row echelon form. And so the precise instruction and precise definition of the row precise instruction is a little complicated, but basically you want to eliminate the rows one by one, so like you are left with only the pivot. Okay, so you see the first row as a pivot, then you eliminate everything after this first element, and you get this, and then you find the next pivot element of the second row, and then you eliminate every element here, etc. And finally, you get this row echelon form where you have a whole bunch of zero like this here, and you got a whole bunch of pivots here, and you also multiply each row, the starting of each row, with a real number, so that they start with 1. Yeah. So this is a row echelon form, and we have done this many times. Hopefully you are familiar with this. And here we are thinking about linear systems, so we are doing augmented matrix. We will also do a row operation on those pieces. Okay. And so that's the this is a Gaussian elimination, and you get a row echelon form, and there is an even stronger one, where you want a pivot to be the only non-zero element of each column. So you kind of do this elimination backward from each pivot. So you eliminate those to 0 and eliminate these to 0. And then we have an example here where you start with this augmented matrix, and you get a row echelon form like this. Then you backward elimination and get a reduced row echelon form like this. Okay. And here are the definition of a row echelon form. If you want, it's really long, and the definition of a reduced row echelon form. And we also talk about overdetermined system and undetermined system. Wait, where do I? Oh, I forgot. Okay, I copied it wrong. Okay. Anyway, so overdetermined system is a system where the matrix is n bigger than n. And sorry, I have it. So maybe I just do this here. Okay. So then we have underdeterminant, and it's a matrix where m is less than n. But as we know later, this doesn't really say anything about solution. So overdeterminant using the more equation matrix, so it thinks it's kind of hard to satisfy. So basically, we're always thinking about what happens. So this is A, and we're thinking about what are the solution of Ax equal to B. And but later we know that if you want to know what are the solution of Ax, B look like, you need to see the column space of A, right? And so this overdetermined system will say the number of vectors is less than the dimension of the column space of the length of the column, right? So the columns are in Rn, and so there are only n vectors in Rn. So you know that not every B has a consistent solution, but there might be still some B that has consistent solution. So over the determinant, you think. You think sometimes it's not consistent, but it can still be consistent. And those columns can even be linearly dependent, so that when you are consistent, you have infinite solution. Okay. And similarly for underdeterminant, now, okay, so underdeterminant actually, so underdeterminant you have more, you have more vectors than a dimension, and you kind of feel like all those columns should span the whole space, but obviously that's not true. They can still only span a subspace. So once again, Ax equal to B is not always consistent, but here we know something. We know they must be linearly dependent, okay? Because you have more vectors than dimension. It must be linear dependent. So when you have solution, then you must have infinite number of solution. Okay. So that's okay. So I should fix this underdetermined. Okay, so that's this thing. And finally, so 1.2, we give the most important algorithm of the whole class. That's the Gaussian elimination. And although we never give a detailed instruction, but we should have done this many times, and this is something you need to know how to do. Okay, so we have a Gaussian or Gaussian-Jordan elimination, and get a reduced row echelon form or row echelon form. Okay, and once we get this, we can calculate a lot of things. And only 1.2 only know a few bits of them. Okay, so first is you can determine whether it's consistent or inconsistent. If consistent, you can find a solution. So yeah. So you take your ax equal to b, and so you take your ax equal to b, and then you do the Gaussian elimination, and you basically get ux equal to some e of b. Let's just say e prime, right? So you get Gaussian elimination, and so you actually do this in augmentative matrix, but basically you get ux equal to some b prime, and then because this reduced row echelon form matrix is a really strong constraint, so you can read the lead variable and the free variable with u, and I guess so to determine whether it's consistent or not, you just see that. So back to this example. To determine whether it's consistent or not, you just read all of those 0 rows, and if 0 rows correspond to non-zero b, then it's inconsistent, etc. Okay, and and as we know, you can do a lot of things from Gaussian elimination, so you can see whether it's consistent or not. And if it's consistent, then you can also solve the solution, say from ux equal to b prime. And then we have this concept of lead variable and the free variable. So lead variable are basically the color indices that correspond to those pivots. So those places where you have this transition happen, those ones. And the other variables are free variables. Okay, big. Then over determinant, under determinant we say, and we have a definition of homogeneous system where that's just ax equal b when b equals 0. Yeah. So ax equals 0 is a homogeneous system. And we have seen later that homogeneous system is very nice to characterize when you have infinite solutions. Okay, and then next we have matrix multiplication. This is also something you should be very familiar by now, but just do review once again. Matrix multiplication. So matrix are block of numbers. So you can have a matrix A that's n by r, and B r by n, and you can multiply them. And the important thing here, so in order for matrix multiplication to be even defined, you need to have those r equal to r here. Okay, so the second dimension of A must equal to the first dimension of B. Okay, and we have this element-wise definition. So basically, then the resulting matrix AB will be n by m dimensions. So these r kind of disappear. And but R is useful when you calculate element of AB. So the ijth element of AB will be the ith row of A, and doing scalar product with the jth column of B. So you take the multiplication with element one by one and then together. Okay. So that's matrix multiplication, and there are a lot of okay. So that's probably the most important operation you can do on matrix. So matrix multiplication, and important thing to remember is in general it's non-commutative. So AB is not equal to BA. So it's different from scalar multiplication. And we have other matrix operations, but now you should be very familiar. So equality, two matrices equal to each other if every element equal. And you can multiply a scalar on the matrix. You can adding two matrices together. Then you can add. Then there are addition, identity, and addition inverse. So those are the special cases from the vector space we know, right? So vector space identity and inverse, and then you can think about matrix addition, identity, and inverse. Okay. And there are scalar product, which will be probably useful later. Just writing here. So scalar product is you have where am I? Okay. Scalar product is you have a column matrix, a column vector and a row vector with the same dimension, say n. And then basically you do the matrix multiplication on them, and you will get some number, right? You get some number here. So you add those together and then one by one together. So it's equal to some like AI, BI. Okay. So the scalar product will be useful later. And then we have linear combination, which we spend a lot to talk about in chapter 3. So linear combination with some vectors is something like this. So you have some scalar coefficients times your vectors, and you add them together. Okay. And then there's matrix transpose. It's a pretty easy operation. Basically, you swapping a row and columns of matrix. So you have some matrix like this, and you have some rows, you have some columns, then you transpose, and you get these matrix, and you swap the row and column. And a symmetric matrix is a matrix, well, it must be a square matrix because the number of row equal number of column, and it's a matrix where its transpose equal to itself. And then we have matrix algebra. So here are some rules about the addition of matrix and its multiplication with scalar, addition multiplication of matrix and scalar multiplication of matrix. It's basically what you expect, kind of like a scalar addition multiplication rule, except the matrix multiplication are non-commutative as we said. Okay? So there are matrix algebraic rules, most of them are linear, etc. Yeah. And okay, so those are easy. So you have identity matrix. It's just a matrix where it's one on diagonal and zero everywhere. And then we have the matrix inverse property. So we divide this inverse as a matrix where A inverse A times A equal identity. And we say there's a theorem says that if you satisfy this, it also satisfies this. So A inverse equal identity. And I guess a little thing to stress is matrix inverse. We only define it on n by n matrix. So some of the property in the first chapter only defined on n by n matrix, and it's one of them. And I think basically everything related to this, yeah. So only define on square matrix, and yeah, and we know that later we'll say, so there are yeah, so we'll say matrix with inverse is invertible, and then we have a singular matrix equal to non-invertible matrix. So the singular is also only for n by n matrix. Okay. And anyway, we have a property of the inversion, and we know that the A inverse is unique. And also your product of two invertible matrix is also invertible, and its inverse is B minus 1 and minus 1. And also you have similar rules for transpose. AB transpose equal to B transpose A transpose. Okay. Then we have the, okay, so that's a little digression. Then let's back to kind of Gaussian elimination. Okay, so we define Gaussian elimination in this mole matrix form. We define the elementary matrix, which are basically doing the, okay, so there are three elementary matrix. E1 correspond to type 1 of the row operation, so you change the ith row and jth row. And type 2, you multiply a row by some number alpha. And type 3, you add a row to another row m times. Okay. And so three elementary matrix, so they correspond to three row operation. And elementary matrix, you can get it by do the row operation on identity matrix. And the important thing is you multiply elementary matrix on some matrix A, then that corresponds to doing that row operation on matrix A. So you can just use in multiplying elementary matrix to do row operation. So, and yeah, they are invertible. They are all invertible. Okay, and okay, let's keep talking here. And row equivalence of two matrix. So that's basically the, similar to the concept of equivalence of a system. And anyway, row equivalence means that you can find a whole bunch of elementary matrix to connect one matrix with another matrix. So you can do row operation on one matrix to get the other matrix. And yeah, so those two matrices will have similar solutions. If they are, I guess they have the same solution for Ax equal to 0. Yeah. But anyway. So yeah, those are row equivalence of a matrix, and then we have then we find out, so using this row operation on the matrix, we find out that we can calculate a minus 1 by Gaussian elimination. Okay, where are we about this? Okay, so here is how you calculate a minus 1 by Gaussian elimination. So you write a kind of a big augmented matrix. So you have A here, and you put identity here. And you do row operation to turn A equal to the reduced row echelon form. You basically turn and A is veritable, and they can get to identity. So you get this equal to the identity matrix, then the other side will become A inverse. Yeah. This can be proven by these elementary matrices. Okay. So we see that A minus 1 can also be calculated by Gaussian elimination. And then we have conditions for non-singularity, and once again, remember singularity only for n by n. So this is three things are only for n by n. Okay, and so it's this 0, 1.5, 1.2, 1.5.2, and corollary 1.5.3. So it's non-singular if only if x equals 0 has a trivial solution, and if only if if x equals b has a unique solution. Okay. So we have those things. And but later we can kind of see that well, it's n by n, so it's kind of a special case. So the chapter 3 thing, we see that I guess there is a set of things. Okay, so those are all. So A is non-singular also if only if you can row equivalent it to the identity matrix. Yeah. And later we see that the second one can also have characterization when A is not square. So when A is not square, this means that the columns of A are AOI. So of A are AOI. Okay. Yeah. So columns of A are AOI, and you can kind of feel that it's the same as A and C. So columns of A are AOI. That means you go to reducible error form, and you should have you should only lead variable, and if you have only lead variable in if you only have lead variable in a square matrix, then it must be identity matrix, and also that means A is non-singular. Yeah. That one is a little harder to see from AI, but basically yeah, basically non-singular means that all the columns form a basis and all the rows form a basis. All the I guess the logic here is a little circular, but anyway, you can feel that this is a special case describing the general case where A is equal to 0 only have non-trivial solution, only have a trivial solution. Yeah. And yeah. Anyway, we have three other definition of matrix. So upper triangular means so we can just draw here. Upper triangular means that the matrix has something here, and the lower part is 0, and lower triangular means matrix is something like this, and upper part is 0, and diagonal means both upper triangular and triangular, so we only have non-zero thing on the diagonal. Okay. Okay. Question. Okay. We are a little slow. Okay. And then 1.6 says that sometimes we can view matrix as blocks, and so basically, remember matrix multiplication look like this. You have n by n matrix, and n by n matrix can multiply each other. And if you partition this n part by the same partition, and you can also partition the r part, and you can do the matrix multiplication kind of block by block, like this. So you partition the n part like this and r part like this, and so this n part like this and n part like this, they fit each other, and then you can partition the n part whatever and r part whatever, and the resulting matrix will have the same whatever partition. So here is the example. So you partition this into 2 by 2, the second matrix 2 by 2. Then the first one you can kind of do the block multiplication. So this will be the first block. So this kind of do this. So you kind of look at the block like how you do matrix multiplication. So the first block will be this this block row times this block column. So it will be A11 times B11 plus A12 times B21. And remember, those are all matrices. And so then you do matrix multiplication to find out what are these and what are these. Okay, so that's boxing. And then we go to determinant. And remember, this is about determinant is about whether this failure matrix is invertible or not. And so this whole chapter 2 is about unbounded matrix. Okay. And the determinant, we give this recursive definition. So you get a matrix, and you can expand it really on any row and column. Although we give a definition of expanding on, I believe, the first row. Okay. Anyway, you can expand this on any row and column, and so you have the element of that or the column times this cofactor and adding together. Okay. So you have those elements and times the cofactor, which is equal to minus 1 to the I plus j times the determinant of this smaller matrix. Okay. The small matrix is delete this row and delete this column. So you have this element aij here, and you delete the whole row and the whole column, and the resulting matrix is some mij, and you find the determinant of it and times the minus 1 to ij. So that's the cofactor. So you need to multiply that cofactor with your element and add through a whole row or column. That's your determinant. Okay. So determinant, and it's defined by cofactor expansion. And then we have some special case, and determinant at equal to determinant a. And if you are triangular, then the determinant is just a diagonal. And you have a whole row column is all 0, determinant is 0. And if 2 rows of column are the same, the determinant equals 0. Okay. And this one we'll see a bit later. Okay. And yeah, so we'll see later this. So instead of doing the recursive definition, we can also once again use our Gaussian elimination to calculate the determinant. Okay. That is, you find a whole bunch of row operation and reduce your matrix A to this row echelon form. Okay. And if the row echelon form has a row of zeros, then your determinant is just 0. If not, then the determinant of this is 1 because it's a triangular matrix. Okay. And then because the determinant or product of matrix is equal to the product of the determinant, then you can just calculate this as minus 1 over determinant of all those rows. Okay. And yeah, and the determinant of the different row operations are like this. The swapping row, you have determinant minus 1, and multiply by row by alpha, then just determinant is alpha, and if you add or subtract a row, determinant is doesn't change, it's 1. Okay. Yeah, so you can calculate determinant A also by Gaussian elimination. And here we have an important thing. So determinant is really about whether A is singular. So A is singular if only if determinant A equals 0. Okay. And also we have this important property: determinant A times B equals determinant A times determinant B. Okay. Then finally we have 2.3. And first we define a joint matrix, which we have an example here. So the joint matrix is basically you put the cofactor all together as a matrix. So here you can see A is here, and the cofactor, so A11 is a cofactor of 2, so it's the determinant of this matrix. And say A21 is, okay. And yeah, you have all the cofactors, and yeah, and say A21 is the cofactor of this one, and it's the determinant of this matrix, and it has a minus 1 because it's the 2 ones element. Okay. And then the adjoint of A is all those cofactors put together, and you need to do a transpose. So remember to do the transpose. Okay. So we have this adjoint matrix A, and it's pretty nice because you can use it to find the inverse of matrix. So inverse of matrix is just a joint matrix and divided by the determinant. Okay. And once again, this is this can be only defined when determinant not equal to 0, and that's what we expected. So inverse is defined only when determinant is not 0. And then we also have the Cramer's rule for solving x equal to b, where xi equal to delta of ai. Okay, and okay, I forgot to put the slide here, but it's ai. AI is well, you can look up the slide. So this AI is you have yeah, I believe that's true. So AI I think is A, and you replace the ith column with B. Is that true? That should be. Anyway, yeah, I will have a slide for this AI later. Yeah, that's Cramer's rule. Yeah, so that's one way to solve x equal to b, but obviously you can. We also know we can solve x equal to b by doing Gaussian elimination on this, but that's an extra formula you can do. Sometimes it's faster, sometimes it's slower. Okay, so that's chapter 2 question. Then let's go to chapter 3. So chapter 3 we go to vector spaces. So first we give an example of most familiar vector space, those Rn. So we have an example of R2. So R2 are the set of column vector of 2 elements. Okay. So all vectors like this x1, x2, and we think about it as a point on plane or a vector on plane like this. So x1, x2 has 2 coordinate, and a vector in a plane has 2 coordinate x1, x2 like this. And then we generalize to Rn, then we have these column vectors of n element, and we think it's n dimensional space. So more than 3 is hard to draw, and again, hopefully you can kind of feel it. It's some kind of geometric interpretation. Okay, so that's Rn, the most basic vector space. But then we see that Rn we can define very weird vector space, and we have seen some of it in homework. Okay. So we have this very abstract definition of vector space that is just whatever set of element, and we can with two two operations define it. So addition, you take two vector and get another vector, and scalar multiplication, so for a scalar we just use real number, so we can also multiply a real number on your vector. Okay. And if those 3 things, so there's a set with 2 operations, addition and scalar multiplication, and if they satisfy closure and those 8 axions, then it's a vector space. And closure means you add 2 vector, you get back to you get add 2 vector in your vector space, you get back the vector in your vector space. And yeah, and then scalar multiplication. Also, scalar multiplication on vector in your vector space, you should get back to something in your vector space as closure. And we have A1 to A8, which is, well, it's linear because we talk about linear space. But let's go through once again. So you need to have x plus y equal to y plus x, and you need to have associative. So x plus y plus z equal to x plus y, then plus z equal to x plus y and z. And there is a 0 such that x plus 0 still equal to x, and there is inverse such that minus x plus minus x equal to 0, and so those are only about addition. Then you put the vectors and then you put scalar multiplication here. Then scalar multiplication on x plus y should equal to alpha x plus alpha y. Should have a distributive rule, and so also alpha plus beta on x should equal to alpha x plus beta x, and yeah, and so something people got a little confused in homework is that, so remember this plus and this plus are different plus. Okay, although we all both written as plus, but but intuitively, the first plus is a plus between vectors, and the second plus is a plus between scalars. Okay. And so scalar, the real number plots we already know about. These plots can be whatever plots you define on your vector space. Okay. Although we use the same notation here. And yeah, but these two rules look similar, but they are kind of different. They are distributive, but the plots are on different spaces. So they can look very different when you have some weird definition of vector space. And anyway, and then we have the associative rule for scalar multiplication, so alpha plus beta times beta x should equal to alpha times beta x, and also the scalar 1 times 0x should equal to x for x. Okay, so 8 of them. And so that's the definition of vector space, and on 3.2 we give a definition of subspace. So subspace is a subset of a vector space, and I should say it here. Subset of vector space, and so it's also a vector space, and with multiplication, addition, with the same scalar multiplication and addition rule, and if it satisfies closure, then it's we call it a subspace, because it will also be a vector space, and we have a small theorem says that you satisfy closure, then the other 8 axiom will also be satisfied. And anyway, and we give 2 examples of subsets here, and obviously you also doing homework see a whole bunch of things to test whether they are subsets or not. And we have 2 important subspace. First one is the null subspace of A. So, oh, sorry, that's A is not space. So, anyway, null space of A is a subspace to Rn. No, Rn. And anyway, that's a solution set to A is equal to 0. And yeah, and later we see that, actually here we see that then you can solve for basis for the null space by once again doing Gaussian elimination on A. Okay. And then also span of set of vector is a subspace. So you are just giving whatever vectors, and you think about all possible linear combination of them. And yeah, so you just get a whole bunch of vector v1, v2, vn. And then you can think about span of them. Yeah. And that's all possible linear combination of them. And then you can also think about spanning set of vector space, where a set of vector their span equal to a vector space. Okay. And then we start going to linear independent. Okay. So we start with this conceptual definition of linear independent, that is, where a set of vector, where any one of them can be written as a linear combination of each other, of other ones. And we see that that's similar to the more algebraic expression, that is, you want to solve this equation. So C1V1 summation to CNVN, and they want to see when they equal 0, do you have a non-trivial solution? And we give this as the definition of linear independence. So you solve this equation, so you get a whole bunch of vector. Then you ask whether C1V1 plus to the CNVN equals 0. Do they have a non-trivial C as solution? If there is a non-trivial solution, then they are linear dependent. So those V1 to Vn are linear dependent. If C1 to Cn must be all equal to 0, then they are linearly independent. And yeah, then we have the concept of basis, we will talk about more. Yeah. And yeah, and we have these columns. Okay. So yeah, so we have a square matrix characterization once again. So X is not singular if only if, so for square matrix, X is not singular if only if the columns are linearly independent. And yeah, and also we have this very interesting says that, so basically generalization of this factor. Right? So linear independent means that when your when your linear combination of vector equal to something, then you have a unique, is always a unique solution. Okay. So the linear combination are always unique. Okay. So basically, it is some CI VI equal to some B. This also always has a unique solution. Okay. So where B equal to 0, we have unique solution. B equal to other thing, you also have unique solution. Okay. That's linear independent. Okay. And from these unique solution thing, then we can define our. Why do I? Okay. Then we can define our concept of basis. And basis is a set of vectors that satisfy two things. And you need to span the whole space, and they need to be linear independent of each other. And so then they have this nice property that so they span whole space, so everything in the space can be written as a linear combination of them, and they are linear independent. So so when you write everything as a linear combination of them, you have unique solution, unique coefficient. So you can find this, go a little more to 3.5, you can write everything as a coordinate to it. And so everything inside, so you have some basis here, then anything inside the vector space can be written as some unique coefficient times so some unique linear combination of your basis vector. So you have unique coordinate alpha and beta here. And yeah, and we will need some ordering here for ordering of alpha and beta. So we will also have a notation for order basis. Just do whatever order on your vectors. Okay, but anyway, back to the property of basis. So it spans the whole space and they are linear independent. And we find out that we have this interesting property that if you have a basis for some vector space, then then you have any set of vector that has more elements than your basis. So suppose your basis is v1 to vn. Suppose the basis is v1 to vn. Okay, and they have more elements than this. Okay, then you have some u1 to u maybe n plus 1, and then this set must be linearly dependent. Okay. So yeah. So basically, so then we can define the dimension of a vector space as the number of elements of its basis, because all of them must be the same. So yeah, so n-dimensional space can only fit a linearly independent vector in it. And then we have the intrinsic theorem give you 3 different characterization of basis. So we say if span the whole space and there are only independent its basis. Also, if you know the dimension of the space is n, then either you find n vector that are all linear independent, they must be a basis, or you find the n vector that are all they span the whole space, then they must be a basis. Yeah. Okay. And 3.5 will kind of recurrently say. So the important concept here is coordinate. So if you have a basis for a vector space, then every vector inside you can find a coordinate for it, and then you can transform coordinate between different bases. So we see that you have order basis v1, v2, and so you want to, believe it is transform coordinate from v1, v2 to a standard basis e1, e2. Then you just multiply your coordinate with this matrix V. That's formed by listing those v1, v2 together. And then when you want to transform from e1, e2 to another basis u1, u2, you do this u minus 1. You multiply by this u minus 1. So if you want to go from v to u, then you do this u minus 1 times v transition matrix. Okay, so that's 3.5. And finally go to 3.6 that we just talked about on Monday. Okay. And yeah, 3.6 we give more characterization of the matrix. So there are row space and the column space of matrix. So this space spanned by rows and space spanned by column. And yeah, And obviously, row equivalent means row equivalent matrix have the same row space, and in particular, the reduced row echelon form has the same row space as the original matrix. And we define rank as the dimension of the row space, which we also prove as a dimension equal to the dimension of the column space. And nullity is the dimension of the null space. And they have a strong connection and prove that rank plus nullity equal to n. And so the solution of Ax equal to B can be characterized by how the column space will look like. So if the column space spans the whole Rn, then Ax equal to B always is consistent, always has solutions. And if it's AOI, then it has then when your solution is unique. So if you satisfy both, then first it must be a square matrix, and then you satisfy both, it must be a square matrix, and everything has a unique solution. And you see that the thing as is non-singular because you can just have a-1 to solve this for everything. Okay. So kind of fit for everything. And then once again, Gaussian elimination is very useful. You find out that you can use Gaussian elimination to find a basis for the row space, column space, and null space. Okay. So you get some vector, and you get reduced row ratio form of it, and well, I guess some of them you can do by just row ratio form. But anyway, reduced row ratio form give you a little better. Yeah, it needs more calculation, but although you see something a bit more better. I guess for the null space, you really want to reduce row ratio form. Okay. And anyway, you get reduced row echelon form, then the rows of U will be the basis for your R of A. And if you want basis of column of A, then you need to look up the lead variables. And so the columns correspond to the lead variables in this row of U. In this U will be the basis for C of A. And also, yeah, you can solve for Ux equals 0 to find the basis for null space of A. Okay. And basically, kind of relate to the null granularity theorem. So each variable will give you one basis for n of A. Okay. And 3 minutes. And finally, we have this small example of book question here we can do. And so we are given 4 matrix. And, oh, I guess before I do this, do we have a question? No. Okay. And yeah, so we have 4 matrices in the whole 4 vectors, and we ask a whole bunch of problems on it. Okay. And so first question is whether they are all LI. And okay, so let's try to do this really quickly. And are they AOI? And it's obviously no, we don't need to do any calculation. Okay. And that's because there are 3-dimensional vectors, so they are in a 3-dimensional vector space, and there are 4 of them. So obviously they are AOI because there can only be 3 AOI elements in 3-dimensional space. And the second one is whether the first two, x1 and x2, span R3. And this you also don't need to do calculation, because if they span R3, then because you know you need at least 3 elements to span R3. Okay. And then the third one we actually need to do calculation. So x1, x2, x3, do they span R3? Okay. And so we want to find the dimension of the space and span. Okay. So x1, x2, x3 we listen together, and we do the Gaussian elimination. 1, 2, 2, 1, 3, 3, 1, 5, 5. Okay. And so Gaussian elimination. So you subtract this here, and you see that you get 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay. Wait. Wait, I got a little confused. Okay. Well, they are linearly dependent, but reduced form, we only get one. Oh, sorry. So I do a calculation wrong. That's why the result is really weird. Sorry about this. Okay, and yeah, so you subtract 2 here, and then you get 1, 3, 1, 3, and you subtract here, and okay, so we don't need to go to REF, only go to REF. Okay, so we go to row echelon form, and then you get this 1, 3, 0, 0, 0, 0, 0, 0. Okay. So you see there are only 2 leader variables, so dimension is also only 2. Okay, so yeah, so x1 and x2 is the basis for the span of those 3 things, and you can kind of see it here because, well, anyway, yeah. Yeah, it's kind of because the third dimension doesn't do anything here. But anyway, so they only span the 2-dimensional space. then they don't span the whole R3 because it's 3-dimensional space. Okay, and then you have a 3 vector in a 2-dimensional space, so they are LI, and as we say, they don't form a basis of R3 because they don't span R3. And yeah. So you are over time, but so you can do similar operation on x1, x2, x4, and yeah, then you should see that the reduced form is identity, and so they are actually OI, and it's a basis of R3. Okay, and yeah, so those are midterm review, and any question? Otherwise, we'll do midterm on Monday. Yeah, and hopefully we'll give you all the how we arrange everybody into different classrooms soon. Okay, so we're over time, and yeah, so let's stop here.